Okay. So, what are we going to be looking at? Functions and components. What are all the things that we're going to find in the blood? And we're going to do a big focus to our red blood cells. What are our functions? It's going to move gases. That's pretty obvious, right? Oxygen, carbon dioxide. But it's going to move nutrients. Again, pretty obvious. We're going to move those glucose and that kind of stuff. But we also find hormones in there. Do you remember in the endocrine system, I talked about hormones. You can have bound hormones or unbound hormones. Bound ones last a little longer than unbound. Why? Because there's a lot of enzymes floating in the blood, metabolic waste. Part of the function of your blood, particularly from your red blood cells, is to prevent your blood from getting too acidic. Do you remember what the acidity range was on the human body? Yeah, 7.35 to 7.45. It keeps a super tight range. Why? Because it denatures proteins. So one of the biggest factors that makes us acidic is CO2. If we get too much CO2 in our blood, it drives our acidity levels down. So your red blood cells have a way of taking carbon dioxide and basically turning it, doing a buffering system. Do you guys remember what buffers do? What do? They resist changes in pH. So we take carbon dioxide into the red blood cells and we spit out a chemical that's going to prevent us from getting really acidic because of the carbon dioxide. So we're going to look at that today. But that's where we get into this regulation of pH. Who's our big pH regulators? Red blood cells. We give them all the credit for oxygen transport, but they're actually our big buffers to our blood system as well. I'm sorry, go ahead. Buffers help to prevent dramatic swings in pH. Kind of keeps your pH values consistent. And we know we don't want to swing outside of this range. We're also going to see restricting fluid loss at injury sites. So basically, we're going to clot our blood if we get injured, and we'll look at how that happens. We're going to defend against toxins and pathogens. That's the job of our white blood cells. And then we're going to stabilize body temperature. Why? Because we pick up heat. Who's our number one heat producers in the body? Muscles, right? And we're going to pick up that heat and put it in the blood. If we're hot, we can route it through the blood to the closer to the surface area of the skin. If we're cold, we can route it deeper and keep it deeper in the body to keep us warm. So those are kind of our big functions of our blood. Oh my goodness. There we go. All right, 38 degrees Celsius or 100.4 is pretty common temperature for your blood. It has high viscosity, so it's kind of thick, and it's slightly alkaline. Here's our range. You should know this range right here. Blood volumes, it's about 7% of body weight. This is probably kind of important to know. Around 5.25 to 5.4 quarts of blood is about average for kind of an average sized person. Obviously, probably men are going to run a little bigger most of the time on this side, women probably a little under that. All right, whole blood. Your whole blood, it has plasma. Plasma is going to be the fluidy part. And then it's going to have stuff that's floating in it. That's going to be our formed part. What's some of our formed stuff? Our cells, our red blood cells, our white blood cells, proteins, things like that. Fractionation, when you hear that term, it's basically where we just take whole blood, we can spin it down, and we can separate the formed particles by spinning them to the bottom, and we can leave the fluid on the top. And that is fractionation. We're basically splitting it from formed and fluid part. Plasma makes up 55% of your blood volume. You should know that. 90% of plasma is water. And I know we've kind of touched on this a bit because we've talked about how can we regulate blood pressure. We've talked about the kidneys already, right? We can turn up the volume by putting more water in the blood, or we can turn the volume down by taking water out of the blood. So that's one way we can regulate blood pressure, is regulating the amount of water in our blood. It also has a lot of plasma proteins, and I think people don't realize that we have all those plasma proteins in there. We already know one function of those plasma proteins. It attaches hormones and carries hormones, right? Because we kind of talked about that with the endocrine system. So we'll look at some of the functions of those proteins. It is very similar to interstitial fluid. Why? Do you remember if you had me for 201, I was drew this picture for you when I talked about the lymphatic. And I said we go to arteries, to arterioles, to capillary beds, right? And this is where we basically use hydrostatic pressure, which is volume pressure, to push things out of the blood vessels, and it goes into the tissues. So what goes into the tissues? The fluid from the blood. We just change its name. We go from plasma, as soon as it pushes out of the blood into the tissues, it becomes interstitial tissue, or I'm sorry, interstitial fluid. And then when it gets picked up by the lymphatics, we just change its name again and we call it lymph. It is the same fluid. It goes from plasma to interstitial fluid to lymph. That's all the exact same thing. So would it make sense that it's the same composition? Yeah, because it's the same fluid. We just changed its name. The biggest difference we'll see in it is what's in it. Because some stuff isn't going to diffuse as easily out of the blood vessels. Some things aren't going to get picked up into the lymph as easy. But it's going to be very, very close, very similar in composition. It is the small stuff that can move between those vessels. The big stuff doesn't. And some of the big stuff that can't move is the plasma proteins. Plasma proteins stay in the blood vessels. All right, and this shows you kind of 7% is plasma proteins. Water's the big bulk. That is important to know, is that it's water. Out of our formed elements, this is an important number to know. I would know this. Out of your formed elements, 99.9% of it is red blood cells. So most of the solid stuff in your blood is red blood cells. White blood cells is less than 1%. Platelets is less than 1%. What do platelets do? Clotting, they're clotters. All right, albumins. This is important to know. It is the most abundant of the plasma proteins is your albumins. They contribute to osmolarity. They also do a lot of transportation of hormones. So remember when we were talking about active thyroid hormone, inactive? Inactive thyroid hormone goes and attaches to an albumin. So this is the most common plasma protein found is our albumin. When we talk about plasma osmolarity, and it gets a little bit complex, we have kind of two ways. We've talked a lot about concentration gradients, right? Back even in 201, we talked about the sodium potassium pumps, and we move things using concentration gradients. There's two types of concentration gradients we really focus on, and it's how your body functions. One is a pressure gradient. If I turn up the pressure, if I have a vessel and I turn up the pressure and my pressure is higher in here and I have fluid in here and it's lesser out here, it's like cranking up the spigot on my hose, right? Stuff is going to spray out of here because of pressure. We call that hydrostatic pressure, or we're using a pressure gradient to move things out. The other way we can move things is using solutes. Remember hyper, hypo, iso? If I have more proteins or particles in here than I do out here, how's my fluid going to move? Inside. So those are two big pressure gradients. We call this osmolarity gradient. Osmolarity. So we're moving things based on particles. So we can either move it using volume pressure, or we can do it using solute amounts. So albumins are not big enough to transport in and out of vessels. So if we diffuse a lot of stuff out, albumins are going to encourage fluids to come back in, because now we're going to have all these solutes. If we diffuse the fluid out, and we're going to move things back into where the solutes are. So these plasma proteins play a really big part in this right here. Globulins are probably the second most abundant. They carry a lot of your antibodies. Again, they do some of your hormone binding proteins. This is probably an important thing to know. You might want to put a little star by it. It does your metalloproteins. That's the big one. Your steroid binding proteins. Remember, steroid hormones are lipid soluble. So when you see this lipoproteins, these kind of go together. Metalloproteins. Yeah. Just another form of protein. Yeah, they bind, just a binding protein. Everybody good? All right, fibrinogen. If we see O-gen on the end of it, what does that mean? It's inactive. So this is the protein that when we activate it, helps with blood clotting. I always say this is like a little chemical net, like if you think of a fishing net, but it has a lot of holes in it, and we clog up the holes when we activate it. So fibrinogen is kind of floating around, and if we activate it into fibrin, now it becomes like my fishing net, and my platelets will come and dam up in this net, and this is how I clot blood. But until I take fibrinogen and turn it into fibrin, it's not going to let anything stick to it. So this is my inactive blood clotting chemical. When I activate it, I'm going to call it fibrin. And now it's going to be like the net that all the platelets are going to clog into. And then there's other plasma proteins. Those are the big three you should know. Oops, sorry about that. So know your albumins, your globulins, and your fibrinogen. Most of your plasma proteins are made in the liver, and that includes all these ones we were just talking about. Antibodies are made by plasma cells. Peptide hormones are by endocrine organs. All right, what are your formed elements? Red blood cells, white blood cells, and our platelets, basically. Hemopoiesis is basically the process of making different formed elements in the blood. And hemo means blood, poiesis means basically to form. Everybody good? All right, here's our platelets. Platelets are interesting because these are important for clogging. With platelets, we start with a cell called the megakaryocyte, and it's this giant cell, and basically it just kind of gets exploded into a whole bunch of different fragments. So these guys are just pieces off of this big giant cell, and so they're teeny tiny little fragments floating around. These are the guys that will stick to fibrin if it becomes activated. All right, white blood cells. These are called leukocytes, is the big umbrella name. And under our umbrella, we have neutrophils, eosinophils, basophils, lymphocytes, monocytes. What's important to know, the most abundant of the white blood cells are the neutrophils. These are what we're going to find the most of when we're talking white blood cells. Are there very many white blood cells compared to red blood cells? Heck no. There's 99.9 of them are red blood cells, right? But on the few little percentage of white blood cells, neutrophils are our most abundant. All right, and then here's our famous red blood cells. Couple important things to know about red blood cells. They are concave in shape, which serve to give them lots of surface area for exchange. They also are anucleate. They do not have a nucleus. Why? Because it takes up space, and we're making them in the bone marrow. We really don't need a nucleus. So red blood cells, because they don't have a nucleus, they don't have DNA, they can't build protein, so they can't repair themselves. So as a red blood cell becomes damaged, it just gets taken out of circulation. Who takes it out of circulation? The spleen is one of the big places that take damaged red blood cells out. But we can take them out within the vessels and other areas of the liver, some other areas in the body. Spleen's a big one. Iron is a component. So our red blood cells have all these hemoglobin molecules, which are proteins. and they have every hemoglobin molecule has 4 iron binding sites. Iron is a scarce commodity in the body. So even though our red blood cells aren't living very long, when we break them down, when they're damaged and they're beyond repair, we don't throw the whole kit and caboodle out. What they'll do is they'll break them down, they'll recycle amino acids from them, but they'll take those iron that were in the hemoglobin and they basically ship the iron back to the bone marrow and we'll put it in a new red blood cell. So we do recycle our iron out of our red blood cells because, again, it's a super scarce commodity in the body. All right, red blood cells, we said 99.9% of our formed elements. I just talked about hemoglobin. Hemoglobin is a big globular protein. You have lots and lots of hemoglobin in one red blood cell. Each hemoglobin has 4 binding sites. Each binding site has iron kind of at the center of it. It is the red pigment of hemoglobin that gives whole blood its red color. When it is oxygenated, it takes on even a brighter red appearance. When it's deoxygenated, it takes a darker red, almost a bluish purplish appearance to it. Our hemoglobin will bind oxygen. It will also bind carbon dioxide, which nobody gives it credit for that, but it does. Red blood cell count. This you should probably know. I put a little star by it. For males, 4.5 to 6.3 million. Adults, 4.2 to 5.5 million. You should know what hematocrit is. It's basically your packed cell volume. And you should know this. So if we put all those blood cells together, we kind of spin them down and look at them. Males should be about 46, females about 42. And I think I have a picture of this for you guys. If you go into healthcare, you'll probably get familiar with some of these numbers and terms. I was having trouble understanding hematocrit. It's basic. I think I have a picture of it. No, I guess I don't. It's basically when we take all the formed elements and we spin them down. They look at, they just look for a number of what is there in your blood, not in percentage, but the amount of red blood cells, and they just assign it a number. So it's just oh, well, this is all formed. Your hematocrit is all, I think I said red, but it's all blood cells. My apologies on that. Everybody good? But of all of those, the bulk of them are red blood cells. Okay, I said red blood cells are that concave shape on both sides, which is why they say bioconcave. The purpose of that is to increase surface area. Why do we want increased surface area? So as we get exposed to gases, we can easily do this gas exchange. And this shows a blood smear. We don't see any white blood cells here, but these are red blood cells, and these teeny little dots in here are your platelets. So remember, we took a cell and we kind of blew it into a whole bunch of little pieces. These are the little pieces. And this is what they look like. This is with an electron microscope. And just to point out, I'm going to talk about this in a minute. I'm going to talk about a roulet. These red blood cells will stack up like this into single file lines like this, which we call a roulet. And you're kind of starting to see that right here a little bit. Where do we really see these single file stacks? When we get to the capillary beds. So when we're in arteries, it's like a super highway where we have, I don't know if you think of a highway, we have 59 cars traveling all side by side, some in front of each other, some not in front of each other. As we get smaller and smaller and smaller, this would be like getting to my one-way street. Now only one red blood cell can pass down the street at a time. What would be the advantage of that? Where's our exchange take place? Right here, right? So by going single file, now that one cell has full exposure to the tissue around it, which is going to allow that easier exchange. If I had 59 cells passing through at the same time, some stuff's going to get missed along the way. So we basically are taking our superhighway and we're turning it into a one-way road down here. And when we get to our one-way road, all of our red blood cells will be in stacks like this, and we call them rouleaux. This just shows the concave function of it. Again, it's for surface area. Why do we want big surface area? For that gas exchange, that rapid and easy gas exchange. Here is our rouleau term that I was talking about. This is when we get nearer to our one-way roads and we're taking them through in a single file stack. We call that a rouleau. What's the function? Big surface exposure with our tissues. And then how does stuff move? It moves using concentration gradients. It's going to use hydrostatic pressure, which is turning up my volume. I turned my spigot up really high. But it's also going to do it based on concentration gradients of what is where. If I have more oxygen in my vessel than I do in my interstitial tissue, where's oxygen going to move? From my blood vessel into my interstitial tissue, right? If I have more carbon dioxide in my interstitial tissues than I do in my blood vessels, carbon dioxides, they're going to trade like that. They're going to follow the concentration gradients. One thing I'll just mention that I didn't talk about is red blood cells are super flexible. They can bend, they can diffuse in and out of areas, which makes it easy for them to pass through these little single file roads everywhere. All right, and this shows some of my single file rouleaux here. They are anucleate. We just talked about why are they anucleate? Because it's heavy. It would take up volume in the cell. So we wouldn't be able to transport as much hemoglobin, which means we couldn't transport as much gas. So they lack mitochondria, they lack ribosomes because they can't make proteins because they don't have a nuclei, which means they have no DNA. If they have DNA or don't have DNA, they can't make proteins. Ribosomes make proteins. So it kind of makes sense that they don't have all of this stuff. A long living red blood cell will live about 120 days. Which really, some of them, they don't all obviously get born the same day and die the same day. So we'll see swings in our red blood cells here in Colorado is a big thing we'll talk about, like with high altitude training. You come from sea level to Colorado and now all of a sudden people can't breathe. How long does it take to adjust to our altitude? Usually about 3 weeks. How long does it take to go the opposite direction? Usually days. How long does your high altitude advantage last? Not very long. Like when that's why they train here, but when they travel for the Olympics and things like that, they lose that high altitude advantage pretty quickly. It is. Your kidneys secrete erythropoietin. When it is erythropoietin, when we are hypoxic or have hypoxia, which is a term you should know, I think we're going to talk about it. But hypoxia just means, hey, we don't have enough oxygen. So if you have hypoxia, the chemoreceptors in your blood will pick that up. And the kidneys and the liver, but it comes really strongly from the kidneys, will secrete EPO, which is erythropoietin, which basically is the chemical that says go secrete more red blood cells or build more red blood cells. Normal hemoglobin in an adult is 14 to 18 grams per deciliter. Females is 12 to 16 grams per deciliter. So this is how many proteins in our red blood cells can be transporting our carbon dioxides and our oxygens. If we have under normal, we are going to use the term anemic for that. If we have the normal range, we're going to be doing, we shouldn't see hypoxia. When will we see instances of hypoxia? If we do big altitude changes. Why? Because we don't have as much oxygen in the atmosphere, and our breathing and our oxygen intake also works on concentration gradients. All right, so hemoglobin, I said it was a big globular protein. It's a quaternary structure. Do you guys remember this from Bio 111? We talked about primary, secondary, tertiary, quaternary. Quaternaries are we have multiple proteins. They bend and they wind and they twist together. You don't have to know about the alpha and the beta chains. Just each of these globular proteins has a hemi in it. Each hemi has one iron. So there's basically like 4 hemis per iron, or I'm sorry, per hemoglobin. Iron is what really interacts with the oxygen. It's kind of the binding site for that oxygen. So oxygen will come and bind to that iron and it makes oxyhemoglobin. It disassociates, so it can separate itself from iron pretty easily. And when oxygen leaves iron, it forms deoxyhemoglobin. So this is iron with an oxygen on it. This is iron without an oxygen on it. So oxyhemoglobin, deoxyhemoglobin. And this shows my quaternary, my big globular protein. Here's my 4 binding sites, my hemis with iron on them. Yes. It just has a higher affinity for, and I don't know why, but it does. So, and that is a big thing, even more than carbon dioxide. And so what it does is carbon monoxide will attach to these and it won't disassociate. Yeah, it won't really disassociate at all. It binds so hard to iron. So now we're not getting rid of it at the lungs. And pretty soon, basically you suffocate with carbon monoxide poisoning. Why? Because we don't have enough. Pretty soon all these guys are full of carbon monoxide and we can't bind oxygen. So, but I don't know exactly what it is that causes. You probably have to ask your chemistry teacher, but it has to do, I'm sure, with your electrons and that kind of stuff, but I don't know the exact molecular makeup of it. Fetal hemoglobin. Fetal hemoglobin has even a higher affinity to attract oxygen than adult hemoglobin, which makes it where as your mom's red blood cells come to the placenta, the oxygen will go to the baby's hemoglobin off of mom's hemoglobin because it has a stronger affinity, a stronger pull for oxygen than even mom's, which is a good thing, right? Because if it didn't, mom's would just hold on to the oxygen, but instead we cross the oxygen across the placenta and give it to baby. But because of this, because we have baby internal fetus red blood cells that have this high affinity for oxygen, when a baby is born, and they kind of do this switch over from baby high affinity hemoglobin into regular hemoglobin. And that breakdown, when we break down red blood cells, and we go from kind of baby fetus red blood cells to adult red cells, part of what is created in that breakdown and that switchover is the bilirubin, and babies then that are jaundice have those high bilirubin counts, and it's because of the bilirubin is a sign of breaking down those red blood cells. And so as babies switching over, they're breaking down a lot of red blood cells. Colorado is one of the highest jaundice states we have, and the belief is because we have a high amount of red blood cells because we're at such a high altitude, then babies really breaking down a lot of fetal red blood cells, and so our babies tend to be jaundice more than other babies. There's about 280 million hemoglobin molecules in each red blood cell. Isn't that crazy? 4 iron molecules for each of those. So lots and lots of iron. And again, it's kind of a scarce commodity. So each red blood cell can carry over 1 billion molecules of O2. All right, how does it work? It follows concentration gradients. So if I got here to my capillary bed, which I had drawn over here and I erased them, oxygen is low in the tissues, high in the blood vessels. Why? Because it came from the heart, it came from the lungs, it's highly oxygenated. as we get out into the capillary beds, we've used up the oxygen that's in the tissues, right? The oxygen diffused into the cells, into their mitochondria. They did cell respiration. They made ATP, right? Every cell is making ATP if it has a mitochondria. So we're using up that oxygen in the cells, and we're kicking out carbon dioxide, right? Cell respiration requires glucose. It requires oxygen. What's its byproduct? CO2 and water. So cells are kicking out CO2 and water, and they're taking in oxygen and glucose, and they're using it up and turning it into this. So when oxygenated capillaries come along, the tissues are low in oxygen, high in CO2. So we do this exchange. We just follow concentration gradients, and oxygen moves out of the capillaries into the interstitial fluid. Carbon dioxide moves from the interstitial fluid into the capillary beds. It just follows the concentration gradient. This is where we said it can easily bind oxygen, but it also easily lets go of oxygen based on concentration gradients. So we will release that O2. We'll pick up CO2. If CO2 binds to the hemoglobin, it is now called carboaminohemoglobin. That is one way CO2 gets carried to the lungs, is attached to hemoglobin. That is not the only way, but that is one way. And when it gets to the lungs, where oxygen is high and carbon dioxide is low, that carbon dioxide is going to diffuse out into the lower concentration, and it's going to get exhaled, and it's going to pick up O2. So they are just following concentration gradients. Where's the concentration of O2 higher? It's going to move from high to low. Where's the concentration of CO2 higher? It's going to move from high to low, and that's how we do our exchange of our gases. Anemia, this is when our hematocrit, or our hemoglobin content in our red blood cells, is reduced. And if we don't have enough red blood cells or hemoglobin, then we can't bind oxygen. We're going to be hypoxic. We have about 1% of circulating red blood cells replaced today. About 3 million new ones enter the bloodstream each second. So that's a lot. One of the big things they find with anemia is oftentimes if a person has anemia, which really is a sign of low red blood cell count, low hemoglobin counts. So if someone is anemic, oftentimes they are low in B12. They're B6s, B12s. And you need those to help with the formation of those hemoglobin molecules. Erythropoiesis, this is, remember, poiesis means to build. So this is building red blood cells. These start with stem cells. In embryos, we're going to start with embryonic blood cells. And these embryonic blood cells move to areas where we can create blood cells. So liver, spleen, thymus, bone marrow. And they will differentiate. So my embryonic cells will differentiate into stem cells, which can divide to produce any of the types of blood cells that I need. So remember, stem cells are just generic cells. Those generic cells can turn into the type of cell we need. What causes them to turn into the type of cell we need? Exposure to chemicals. One we just talked about was erythropoietin, right? EPO. So if EPO is being secreted, my stem cells are going to make erythrocytes. They're going to make red blood cells because that's what the chemical is telling them to make. In adults, we're going to see this in our red bone marrow for our erythrocytes. Also for our white blood cells as well. All right, hemocytoblasts. These are basically also stem cells. And these can become red blood cells and white blood cells. Lymphoid stem cells become lymphocytes. What are lymphocytes? White blood cells. So they're going to be basically associated with the immune system. Was everybody good? Anybody need more time? All right. A hematologist is basically a blood specialist, and they'll look at all kinds of different stuff in the blood to tell you what's going on with the blood. There are different phases to the red blood cells, and if you ever heard about the bicycler Lance Armstrong, when they were doing their blood doping, basically what they were doing, because they used to take erythropoietin, they take EPO, but then they came up with tests and they could test kind of like they can test for steroids. Hey, they're giving themselves EPO. So they started cheating by pulling their own blood out 2, 3, 4 weeks ahead of a race, and they would freeze their red blood. And then when the day of the race came, they would thaw their blood and they would put their own blood back in. Well, when they pulled their blood out, their body said, oh my goodness, we're hypoxic, we're missing all these red blood cells. So their body would kick off its own EPO, make more red blood cells, but then they would take their own red blood cells and put them back into their body. So now we've really increased the amount of our red blood cells, which gave them a big performance advantage. Why? Because they can carry more oxygen. Because who's the first guy who gets rationed if we're low on oxygen? Skeletal muscles. So if they're biking and they're getting winded, who gets shut down first? Skeletal muscles, which is going to affect your performance. So by adding all these extra red blood cells, they had enough oxygen that they could outperform the other people because their skeletal muscles weren't getting rationed. What they did is they came up with a way to test for these cheaters by starting to test the age of their red blood cells. So now they'll pull red blood counts and they'll see what phase are all your red blood cells in. And if they have this huge abundance of one kind or another, now they know they cheated. Super dangerous to do it. Why? Because now we've thickened our blood, right? We've taken a lot more pack, whole blood stuff, and we took away some of our fluid to add more solid to it. So their blood became more viscous. Some people had heart attacks, strokes, things like that. I don't think it was hugely abundant, but it's super dangerous for your heart and your body to mess with the numbers that much. But these are the different stages of your red blood cell. They become a pro-erythroblast. Remember, a blast is a building cell. So these are building my erythrocytes. They become erythroblasts from a pro means pre basically, and then they become a reticulocyte and then eventually a red or mature red blood cell. So they began to test for these different phases of red blood cells, and that's how now they monitor, especially bikers. I know people, isn't it crazy what people come up with to, but it worked. I mean, they had significant advantages. That's how he won for, I think, 7 times in a row, didn't he? Wasn't it 7 times? Yeah. So this kind of shows the phases. This is your pro-erythroblast. And it just kind of, I'm not going to test you on these various phases, but just be familiar that, and it starts with the nucleus, you'll see, but it ejects the nucleus before it enters the bloodstream. So your reticulocytes, you should probably just be familiar with that term, is where you're kind of entering that bloodstream and they've lost their nuclei at that point. All right, EPO, we already talked about it. It is the hormone that gets secreted when we're hypoxic. We're missing oxygen in our peripheral tissues. What might cause that? High altitude changes, things like that. Blood doping, we talked about, everybody good with that. And I kind of mentioned this, B12s and B6s, along with amino acid, irons, folic acid, which is one of the reasons why you're pregnant. They say, hey, take a lot of folic acid. It helps with the development of all these blood cells and stem cells and things like that. People who lack vitamin B oftentimes will have anemia. There is one special kind called pernicious anemia. Interesting, my uncle actually died of stomach cancer, and before they diagnosed him with stomach cancer, he was so tired, he kept going into the doctor, and they kept telling him, you have pernicious anemia, and they were treating him for anemia. And then it turns out they eventually diagnosed him with stage 4 stomach cancer, and the oncologist that he was working with said pernicious anemia really goes hand in hand with stomach cancer. And he's like, the second they saw pernicious anemia, they should have tested him for stomach cancer. And he said that they don't know if stomach cancer causes pernicious anemia or if pernicious anemia kind of leads to stomach cancer, but they seem to kind of go hand in hand. So this is not a super common type of anemia. Yeah. So that's just what his doctor was telling us, which I thought was interesting. So, as I talked about, we're going to recycle stuff. I said that the spleen is a big recycle. It's a graveyard for dead red blood cells. It is not the only place. It is a big one, but we see the liver and the bone marrow and things like that will also recycle, which makes it where we can live without our spleen. We have macrophages there that go in, engulf those red blood cells. They take out the hemoglobin molecules, and they break it into their components, and we're going to recycle that iron. And remember, our hemoglobin is a protein. Anytime we denature a protein, we'll tend to break it into usable amino acids, and we can recycle some of those amino acids. So parts of this hemoglobin, if it's good, some of those amino acids may also be recycled, but the iron is the big one. All right, hemoglobinuria is basically if you have red or brown urine. It just means you have a lot of breakdown of red blood cells in your bloodstream. And when we have more time during the regular semester, I showed this little blurby on the Lance Armstrong blood doping thing. And that was one of the things they found. There was one race where one of the guys didn't do his blood proper when they thawed it. So a lot of the red blood cells died, but they didn't know that, and they injected it into him anyway. And he was saying he was just peeing out black, brown. And that's what it was, is this right here. They were seeing all these dead red blood cells just being taken out of the body. Yeah, it's not very good for you. Hematuria is basically where you have whole red blood cells in the urine. Oftentimes that's due to some sort of an injury or something. Everybody good? All right, this is where we recycle our hemoglobin, which leads to these bilirubins. So when we take our iron out of our heme, we form something called biliverdin, and it gets converted to that orangish yellow bilirubin. And that's why babies, when they're jaundiced, it's usually they have a high bilirubin count, so they get kind of that orangish, yellowish tone to their skin. It gets excreted by the liver in bile. It also can get excreted in the intestines and basically go out in the feces, but it really goes through the liver is the main point. So what is jaundice? It's a big buildup of bilirubin. It can happen in adults. We hear of it more commonly with babies. And again, I think it's that conversion from that really high oxygen affinity hemoglobin in baby red blood cells versus mom's red blood cells. But basically, we can then convert this into intestinal bacteria. And again, it can be excreted out through the intestines as well. So that's really the two ways we get rid of it. And then our iron basically binds to something called transferrin, which is just going to transfer it back to our bone marrow where it will get put into a new hemoglobin molecule. You don't have to know these guys right here, but you should be familiar with transferrin. But you don't have to know this ferritin, hemosiderin. Everybody good? All right, and this just shows a little picture of it. We can see we're going to break down these guys. We recycle the iron. It gets transferred, and it's going to go back to the bone marrow where it'll get put into a new one. These guys get converted to biliverdin to bilirubin. They go to the bloodstream where eventually they'll hopefully get broken down and excreted. This is the same thing. This shows now our bilirubins come into our liver, which can excrete it into bile. Bile is a fat emulsifier, which will get squirted into the intestines. It can also exit through the kidneys. All right, I kind of talked about this when we did lab on the blood, and I'm probably going to kind of cruise through it pretty quickly. Do you guys feel good about antigens, antibodies, why we coagulate on our blood, all of that good stuff? We know what AB and RH, we call RH our D protein. Everybody good with all those? All right, so there's our blood types. We said this AB is a codominant type, right? So dominant, dominant, codominant, recessive. So let's just review really quick. We would have an A antigen. What antibodies would we have? B. What we'd have a B antigen. What antibodies? AB, we have AB antigens. What antibodies? None. Right. You're exactly right. O, we have no antigens. What antibodies do we have? And A and B. All right, good job. RH positive, we said it's a whole separate protein. You either have it or you don't have it. Nobody starts with antibodies to RH. When do we develop RH antibodies if we're negative? Pregnancy would be an example, but it's exposure. Yep, exposure. If we get exposed to that protein, now our body goes, oh no, it's a foreign protein, and we go and build antibodies, which becomes a problem with baby number 2, right? Gluconogens, these are basically, we're screening those antigens. The immune system is, again, ogens is going to be inactive. If we need to activate it, it's going to become that antigen and it's going to cause agglutination, which is that clumping. And here's our agglutinins. We already just talked about all these. This shows your surface proteins, and I drew that for you guys. A transfusion reaction, basically, if we're not compatible, it can cause agglutination, right? What happens if we get agglutination? Blood cells can't flow in and out. They can't move around. They kind of get all glumped together. And I really like this picture. These are the antibodies. So here's my surface antigens. Here's my antibodies. And this is what happens. They go attached to those surface proteins. And basically, they just kind of glum up the works when they clump. And then eventually they cause these cells to break down. All right, so they always test. They call that a cross-match test. This shows clumping. We did our blood typing lab. Everybody feel good about that. And we talked about anti-serum is an indication that you're positive for it, right? So for this one, if we see clumping in A and clumping in RH, that means we are A positive, because with the anti-serums, the clumping gives us a positive indication for that blood type. And this shows the baby. So here's mom, this is RH. So here's mom, here's baby. Everything's fine the first time. Here's hemorrhage on delivery. When the placenta detaches, you'll get usually some blood exposure. So here comes baby's RH positive, mixes in with mom's, and now mom's body goes, uh-oh, and it produces antibodies. And here comes baby number 2. Oops. And here's the case with baby number 2 is that the blood doesn't cross the placenta, but the antibodies do. And the antibodies will move into baby's blood, which is only RH positive. And basically, it's going to end up breaking and destroying all of baby's blood cells. All right, white blood cells are leukocytes. We said that's the big umbrella name. They do have a nuclei. They do lack hemoglobin. Hemoglobin is exclusive to our red blood cells. What's their job? They're going to do defense. They're going to do defense against pathogens, so foreign bacteria, foreign proteins, things like that. But they're also going to help with the removal of toxins and waste. They also will attack cells that belong in the body but have gone astray. They're kind of abnormal cells, not functioning cells. So we even have cells that will go attack maybe a precancerous type cell, something like that. It's cancers usually when they get away with it. Most white blood cells we find in our connective tissue and organs of the lymphatic system. So our lymphatic organs are going to be like our lymph nodes and our lymph vessels. When we talk connective tissue proper, what do we mean by connective tissue proper? It's like actually physically connecting and holding things together. So a big place we'll see this is like in our loose areolar connective tissue, which is actually sits under almost all of our epithelial tissues, and it's actually connecting those epithelial tissues to underlying tissues. We do have a small fraction of white blood cells that circulate in the blood. But a lot of them live in those connective tissues and in our lymphatic system, which is a big part of the immune system. How are we doing on time? Are you guys okay, or do you need a break? Let's see, what time? You guys want to take a little break? Okay, let's take a quick break. Okay, so how do our red blood cells know what to do? I'm sorry, our white blood cells know what to do. Here, let me move this off here. There's something called chemotaxis, and basically when something occurs, you get a bacteria, you get a cut, something like that, you have little chemicals that your tissues will excrete and your white blood cells will follow. It basically creates this chemical message, and your white blood cells will follow that chemical message to the location it needs to go. And that is called that positive chemotaxis. Some of these white blood cells are phagocytic, which means they engulf and basically eat. They're like the little Pac-Man cells. That's going to be your macrophages. Some of your lymphocytes fall into that category as well. All right, so here's our white blood cells: neutrophils, eosinophils, basophils, monocytes, lymphocytes. These guys are going to fall kind of under that phagocytic one. Is everybody good? We're going to walk through each of them, but are you guys okay? Anybody need a minute? All right. Again, I said to know that neutrophils are your most abundant of your white blood cells, so that's important to know. They're always kind of the first white blood cell, one of the first ones that's going to show up on the scene when something happens. They are 50 to 70% of your circulating white blood cells are your neutrophils. And they have lysosomal enzymes, so they show up on the scene. Do you remember what lysosomal enzymes do? Basically, they will either encapsulate a cell or they'll use their lysosomes to inject an enzyme, which will destroy usually bacteria. They kind of focus on bacteria. They're very active phagocytic. Again, they're those little Pac-Man cells, so they engulf and destroy. They release prostaglandins and leukotrienes, which are going to be chemicals that are basically going to alert other cells that, hey, it'd be good if everybody came to this area. They live in the bloodstream 10 hours or less. And usually when they're battling a bacteria, say you get a cut and then you get pus at that cut, usually some of that pus is dead neutrophils. There's always some casualty in the war with your neutrophils, and they can be your pus to that battle. Everybody good? Okay. It shows your neutrophils. They kind of make this little horseshoe shape. They say they're a bilobe. nuclei, but they basically make this little horseshoe shape. Eosinophils, these are 2 to 4%. You should basically know what they target. And eosinophils are really sensitive to allergens. That's one of their big functions. They also will do kind of parasites. So bacteria, protozoa, cellular debris, allergens. Eosinophils will reduce inflammation that's caused by mast cells. Everybody good? All right, and this shows your eosinophils, your basophils. Your basophils release your histamines and your heparins. I would absolutely know that about your basophils. They are not very common. 1% of your white blood cells are your basophils. Histamine dilates blood vessels. Heparin prevents blood clotting. So basically, we're increasing the blood flow to those areas. So basophils with histamine and heparin really create an inflammatory response because they make it where more blood can go to that location because it's thinner and it's flowing easier. And we've opened up blood vessels. So basophils really create an inflammatory response. These are going to be sensitive also to things like allergens. So if we're having an allergy attack, what do we take? Antihistamines, right? Yeah, because these guys are creating all of that inflammation from allergies, which is caused by these guys in large. Everybody good? These shows your basophils, monocytes. These are large ones. The biggest thing to know about these guys is they are aggressive phagocytes. So they are a large cell, they engulf and they do phagocytosis. We really see monocytes in like loose areolar connective tissue, things like that. These release a chemical that are going to attract other phagocytes to the area, and they attract fibroblasts. So because they're under loose areolar or they're oftentimes found in loose areolar connective tissue, which is the most common tissue sitting under epithelials. Remember, epithelials are outside of the skin and lining passageways. So oftentimes these are going to be things that from a cut, from an injury. And if you guys remember back to 201, fibroblasts are the first repairing tissue that show up on the scene. So our monocytes are going to help break down the phagocytosis on stuff. And then they also attract fibroblasts, which are going to be the start of the repair tissues. And there shows your monocytes. Lymphocytes, these are 20 to 40%. These guys move through the lymph vessels. They're in the lymphatic organs. They move in and out of the bloodstream very easily. They're kind of traveling cells. These are part of the specific defense system. What does that mean? They target something very specific and attack it. The other ones are very generic. These guys are more specific. Everybody good? All right, T cells. 3 classes of lymphocytes. We have our T cells, which do cell-mediated immunity. Basically, T cells are going to attack foreign cells. T cells are called T cells because they mature in the thymus, which is where the T comes from. So T cells mature in the thymus. They attack foreign cells or they control other lymphocytes. B cells do humoral immunity. This is basically blood circulating immunity. And these differentiate into plasma cells. Plasma cells make your antibodies. And then we have natural killer cells. These guys, I would say these are focusing on cells that are natural to the body. So these are cells that belong in the body They're going to detect and destroy abnormal cells. So if we have a cell that's had a mutation, it's not really functioning, it's not doing what it needs to do, these natural killer cells can go kind of take care of it. And we're going to get into these in a lot more detail with the lymphatic system, but it's a good start. B cells, so T cells mature in the thymus, B cells mature in the bone marrow, which is how they get the B cell. So thymus, bone marrow. Anybody need more time? Is all okay? All right, some malfunctions to the white blood cell count. Leukopenia is a low white blood cell count. Leukocytosis is a high blood cell count. And leukemia is basically cancer of the white blood cells. How do we know? We have a really high white blood count. We just have this extremely high white blood count circulating, and they're not necessarily functioning because with cancer, you have abnormal cells. They're not doing their job. Everybody good? All right, leukopoiesis. When we say poiesis, it means to build, right? So we're building white blood cells. Again, we're going to have stem cells. They divide into progenitor cells. So if you hear this term, we talked about osteoprogenitor cells in the bones, but progenitor cells are basically cells that are going to be making their stem cells. And then we have lymphocytopoiesis. This is going to be making my lymphocytes. So just terms to be familiar with. Remember, leuko is the big umbrella name. Under leukocytes, we have our T cells, B cells, basophils, eosinophils, lymphocytes, all of those different white blood cells. Is everybody good? All right, so I talked about B cells come from bone marrow. That's what you need to know. T cells come from our thymus. Thymus, spleen, and lymph nodes are really kind of our lymphatic organs. I'm not going to ask you very many questions about this kind of stuff because we'll get into this more with the lymphatic system. Mostly I just want you to focus on those white blood cells. Is everybody good? All right, these I will ask a couple questions. Basically, these are the hormones that cause us to build more white blood cells. And we just saw there's several types of white blood cells. These are super simple to figure out. Let me show you how. Multi-CSF colony stimulating factors. Basically, if I have multi-CSF, I'm going to go make just about all of my white blood cells. I'm going to make my granulocytes, which are my eosinophils, my basophils. I'm going to make monocytes, platelets, and red blood cells. So if I have multi, I'm going to go form multi types of blood cells. If I have GM, colony stimulating factor, basically the G stands for granulocytes, which again is like my basophils, my eosinophils. And the monocytes, these are my phagocytic type white blood cells. So the GM says, hey, we're going to go stimulate colonies of granulocytes and monocytes. If I just have GCSF, I'm going to be stimulating granulocytes. And then if I just have M, I'm just going to be stimulating monocyte. I'm focusing on those phagocytic cells. So when you see the hormones for colony stimulating, just look at the prefix and it's going to tell you what kind of cell it's stimulating to produce. Does that make sense? All right, you do not have to know this chart, but this just shows you, here's your stem cells. We can turn them into a lymphoid stem cell, which is going to become a lymphocyte, or we can turn it into a myeloid, which when exposed to EPO becomes a red blood cell. It can become a megakaryocyte, which makes our platelets, or if we get that other hormone, GM, this is going to become granulocytes and monocytes. So you can kind of see how the exposure to these chemicals differentiates what cells. But I'm not going to ask you to follow any kind of flow chart or anything like this. All right. Does that make sense? Everybody good with that? All right, platelets are also called thrombocytes, and these are, again are we take one big giant cell and we blow it up into a bunch of little cell fragments, and these do clotting. These circulate for 9 to 12 days. They get removed mainly at the spleen. 1/3 of platelets are stored in vascular organs like the spleen. When do we see platelets kind of get sent from an organ out into circulation? When we have some sort of a vascular emergency. You have a cut and you're bleeding, your blood pressure is going down. We are going to basically immobilize, move out our platelets. Very good. All right, what's the function? They do clotting, we know that. They do a temporary patch on damaged blood vessels, which is basically clotting. And they reduce the size of a break in the vessel wall through clotting. So basically our platelets are clotting things. It can be on the skin surface, it can be on the vessels. We're going to see some other chemicals play into this factor as well. So we'll look at these. Everybody good? All right, thrombocytopoiesis is basically going and making platelets. Where do we make platelets? Red bone marrow. We start with a big giant cell called the megakaryocyte, and basically it breaks into a whole bunch of different parts, but really it sheds its cytoplasm. I like it better to think of it as kind of exploding it into a bunch of little pieces. Everybody good? All right, so thrombopoietin is in charge of platelets. We have interleukin 6, which basically is a chemical message. And that chemical message will get secreted when we have some sort of a vascular emergency. I always say IL messages are kind of little cries for help that tissues will, or other body parts will secrete that chemical message. And when this one goes out, the IL-6s, it says, hey, we've got some sort of a bleeding emergency. We need to make more platelets. We need to get those platelets out there. Platelets get produced when we have our multi-CSF hormone being secreted. Everybody good? All right, hemostasis is basically, we're going to stop any bleeding crisis and get us back to homeostasis with our blood. So if we are bleeding, we have 3 phases: vascular phase, platelet phase, coagulation phase. You should be familiar with those 3 phases. Obviously, we're going to start with our vascular phase. So we're going to look at, hey, we cut a blood vessel. How do we stem the bleeding if we're bleeding out through our skin from some sort of a cut to a blood vessel? And we'll walk through that. If you guys remember back, we talked about negative feedback loops and positive feedback loops. A negative feedback loop, we just talked about it with our endocrine system, right? We want to stay here. If we get out of homeostasis, we're going to secrete a hormone that brings us back to here. If we get out of homeostasis this way, we're going to secrete a hormone that brings us back. So to turn it on, turn it off. That's our negative feedback loop. What is a positive feedback loop? overproduction, we're gonna keep stimulating this big giant reaction until we get a result we want. So with a bleeding emergency, remember it is a positive feedback loop, and I'm gonna show you a picture, and you'll kind of see how all of these factors keep sending signals. Hey, more platelets, more clotting, more this, more that. All right, the vascular phase. When you cut your vessel, the first thing that happens is vascular spasm. What happens? The smooth muscles in your vessels constrict, and they automatically make the size of your vessels smaller. This lasts for about 30 minutes. This hopefully helps to restrict the blood flow to those areas. So we have a vascular phase, we have vascular spasm. Basically, our smooth muscles constrict, make the hole that we're bleeding from smaller. So this shows our vascular. Here we have a blood vessel. It's getting cut, and we see it constrict. So you see the size of the vessel here. Vascular spasm is going to reduce the size of the vessel way down. Then our second phase is our platelet phase. And we want to attach our platelets to, so they begin to stick and pile up, and basically you're going to build like a dam. Platelets will stick to each other. They will also stick to the inside of the vessels, and we basically put a little chemical net across there. But to start with, the platelets begin to stick to each other. That's called a platelet plug. And then basically our endothelial cells, you guys remember what endothelial cells are? They're the inner lining of our blood vessels. So those inner lining cells to our blood vessels expose their basement membrane, which is where they, because that is an epithelial tissue where it attaches to the underlying connective tissue. It basically causes this release of a chemical, a couple chemicals. We are going to see prostacyclin, ADP, endotheliums, which are a peptide hormone, and these cause that more constriction of that blood vessel and cell division. It also causes those inner linings of those blood vessels become sticky. And one of the chemicals we'll see kick into effect is like our fibrinogen, which becomes fibrin. And as it becomes sticky, then the platelets begin to stick and pile up in there. So this shows here basically was our cut vessel here. Here, this shows kind of our positive feedback loop. Well, I'll show you a better picture of that. But the cut lining, here's our endothelium right here. And when it gets cut or damaged, we begin to see the release of these chemicals. And these are some more, I'm not going to ask you these ones, but just know that a chemical is released. Prostacyclin, that one I'd be familiar with. Just know that prostacyclin is going to kick off that platelet stickiness. Okay. Then we're going to begin, once we clot and we heal, we're going to need to break all of that down. So we have a coagulation phase, that's our blood clotting. And that's all you need to know about that. I'm not going to ask you any of these names in here. Just know we're going to coagulate. We have three pathways, extrinsic, intrinsic, and common. I'm not going to ask you this, but what I do want you to just be aware of is we have basically fibrin, which came from fibrinogen, which is going to help to produce that blood clot. And it's chemicals that cause that to happen. That's all you have to know. Is everybody okay? Am I going too fast? Are you guys okay? All right. So this shows your positive feedback loop. I'm not going to quiz you on each of these individual ways, but I do want you to realize that it's a positive feedback loop. So here's our common factor, or our common pathway, I'm sorry. And basically, we're seeing fibrinogen create fibrin. Fibrin, remember how I said it's kind of a chemical net, and then all the platelets are going to stick to it. The extrinsic, it's secreted from damaged tissue. So we secrete these chemicals that say, hey, secrete more of this, which is going to create more fibrin. So this route, this chemical secreted from here is causing more of this. And this one, from our smooth muscle and from that portion of the injury, we secrete this. So we're basically like doubling up and tripling up on all these chemicals, which is creating this positive feedback loop. So that's what I want you to know about it, is basically it's a positive feedback loop. The big chemicals I want you to know in this is fibrinogen and fibrin and your platelets. And this shows kind of a picture. You can see the fibrin, it looks like a little net. And then the platelets begin, and the red blood cells begin to get trapped in there, which stops that bleeding. All right, so once we have our blood clot, now we've got to take care of our blood clot, right? Because what happens if we never dissolve the blood clot and it breaks loose? It can wreak havoc on our body, right? It can go to the heart, it can go to the lung, it can go to the brain. It can cause all kinds of issue. So we have to inhibit clotting once we've gotten everything kind of healed and under control. So we have anticoagulants, and that's all I really want you to know is anticoagulants, with prostacyclin is one of those, which are going to kind of begin to calm down that clotting and dissolving of those clots. Doing messages or time. We're getting on time. All right, everybody good? All right, vitamin K, calcium ions contribute to clotting. What else did we say calcium does that's so important? It's stored in bones, but why do we store so much calcium? We need it for clotting. We need it for sending neural signals. We need it for heart contractions and muscle contractions, all muscle contractions. So how long are we going to live without calcium? Not very darn long. So what I want you to know is vitamin K is a precursor vitamin to some of our clotting factors, things that create the chemicals for clotting. So if we are deficient in vitamin K, some people will bleed out or they'll have bleeding emergencies because they are deficient in vitamin K. So sometimes with extreme bleeding, they'll go in and they'll give injections of vitamin K, why it's encouraging those chemicals that help make those clotting factors. Here's some clotting extremes and bleeding extremes. Thrombocytopenia, hemophilia, thrombophilia, deep vein thrombosis. All right, so then we're going to retract our clot. We just pull it away from the area. And we're basically, as we pull the clot away, we're going to dissolve the clot. And now those other tissues can come in and heal. All right, fibrinolysis. What does lysis mean? Breakdown. So we're going to go break down that fibrin, which is going to dissolve that clot. We're going to basically take the threads that made our net and we're going to break it down. That's all you need to know. Fibrinolysis is part of the process of dissolving our clot. I'm not going to ask you these other chemicals in here. Everybody good? Oh, there was our blood. So that wasn't too bad, right? You guys feel okay about it? Okay, I am just going to start a little bit on the heart. And mostly I'm going to be reviewing anatomy that we've talked about. We won't get, and then on Thursday, we'll try to finish the heart the heart physiology. Oops. And so hopefully as we go through the anatomy, you guys feel like, okay, I know this. This is a good repeat of what we've talked about. All right. The heart pumps about 8,000 liters of blood a day. That's probably a good number to know. That is a lot of blood, isn't it? That your heart is pumping a day. Is everybody good? All right, you have to know your circuits. And we've talked about the circulation of blood through the heart, but I haven't really defined the circuits. There are really three circuits. We've listed two here, but you really need to know three circuits. And I'm probably going to ask you these at some point. All right, so if we have our heart here, and we have the right side of our heart, the left side of our heart here. When blood comes into the right side of our heart, it's deoxygenated, right? So this begins our one circuit. Where did this blood come back from? The body. So this is going to be our system, the end of our systemic circuit. Okay, it dumps into my right atria. It's deoxygenated. The first function of the heart is to oxygenate the blood, right? So I'm going to go from here to here. We go out the pulmonary trunk. From the pulmonary trunk, where did we go? To the lungs, and we got our oxygen. Then we come back from our lungs. This flows behind and comes in here on this side. That is the end of one circuit. This is called the pulmonary circuit. What's pulmonary mean? Lungs. This is my lung circuit. So I'm going to start it in my right atria. Some resources will say you start it in your superior vena cava. I like that it starts in the right atria. So we're basically going to go right atria, right ventricle, to the lungs, through the pulmonary what? But the arteries, right? Because it's flowing away. And then what are we coming back on? Our veins, pulmonary veins. And boom, as soon as it hits here, the circuit ends. That is our pulmonary circuit. Half the heart, to the lungs and back is my pulmonary circuit. Now I'm oxygenated. What's the function of the oxygenated blood? To oxygenate the body, right? So now that I go from left atria to left ventricle and out my aorta, this is the start to my systemic circuit. Right? This is going to the body system. It's oxygenated. So we're going to go from left atria, left ventricle, aorta to the body. And then we come back through the superior and inferior vena cava. That's the end of my systemic circuit. So that's our two circuits, our pulmonary circuit and our systemic circuit. There is one more circuit, which is our coronary circuit. And our coronary circuit is how the heart circulates blood to itself. And basically, remember how I said the heart feeds itself first? So we have our two coronary arteries and these begin to divide into all these different arteries, and the heart feeds itself. So basically, my coronary circuit starts on my coronary arteries, and then they return into the coronary sinus. You guys remember the coronary sinus, right? In the back, that would be the end at my coronary sinus of my coronary circuit, because they would come back through the cardiac veins. So on the back of the heart, we had our cardiac veins that came in and dumped into the coronary sinus. So that is my coronary circuit. So really, our book talks about two, but there's really three. There's my pulmonary circuit, my systemic circuit, and my coronary circuit. And this shows all of our vessels. I'm not going to walk through them there because we walk through them lots of other places. Arteries, we said, take away from the heart, right? Veins come to the heart. Capillaries is where the magic happens, right? This is our exchange site, is at the capillaries. So we are going to see things move out of the capillaries and move in at the capillary beds. Good stuff moves out that's going to feed and nourish my interstitial tissues. The waste comes in and we can take it wherever it needs to go to dispose of it. The four chambers of the heart, we know them, right? What's the four valves of the heart? Bicuspid, tricuspid? Which semilunar? Pulmonary semilunar and aortic semilunar. You got it. The top is the base, the point is the apex. So when we look at our heart, this would be the base, this would be the apex. It sits right in the center cavity of your chest called the mediastinum or the mediastinum. Do you remember when I tortured you with that in 201? And you have to learn the cavity. So here is that center cavity right here. This is the mediastinum or mediastinum. And the heart sits right there in that cavity. Pericardium. This is that outer layer of the heart. It is really a two-layer tissue. You have your parietal, you guys remember parietal and visceral linings. On your heart, we have the same thing. So we have our pericardium has a parietal layer and a visceral layer, and it lies in the pericardial cavity, and it has pericardial fluid in it. This is just kind of to show you the cavity right here of the heart. We're looking down on it. This shows basically our pericardial. So it's a two tissue layer. So you can see there's kind of fluid between the two tissues. So this would be my parietal pericardium. I'd have fluid in there, and then this would be my visceral pericardial. Visceral usually sits on the organ itself. The heart's a little bit different in that it's almost like they're showing here. We took a balloon and we pushed into the balloon because there's a space between those two layers. So it's kind of unique in that way. Pericarditis, what does itis mean? Inflammation of. So this is going to be inflammation of the pericardium. Pericardium is that outer sac, basically. When you have inflammation of the pericardial, when you listen to chest sounds, sometimes it'll be a scratching noise. Why? Because we're hearing basically the friction that's being created there. Cardiac tamponade, this is just basically we get fluid in that pericardial. So if I backtrack to my picture here, we get an excessive fluid here, which basically constricts the heart, and now the heart can't beat. It doesn't have the space to beat normally the way that it would. So we get restricted movement. Okay, auricles, we know what those are, right? We know what the coronary sulcus is. Coronary sulcus, basically, if I was looking at the outside of my heart, I can kind of see these little wraparounds right here that separate my atria from my ventricles. This shows where the heart lies in your chest. Here's my sulcus right here. So here's my atria. It's just these little grooves that separate my atria from my ventricles. This would be my interventricular sulcus. It's a little groove on the outside of the heart between the two ventricles. You can see the ventricle takes up the bulk of the heart for sure. And this shows our real hearts. Here shows our cardiac vein. This would be my coronary sinus, which would be dumping blood into the right atrium. So these are my return veins from my coronary circuit. Not circus, circuit. All right, we talked about the pericardium. We have the parietal layer, the visceral layer. We have myocardium, which is our muscular layer. And then we have endocardium, which it lines all inner surfaces of the heart. So when we looked, especially on our sheep hearts, and we could see that really slick, shiny coating on the inside, that's your endocardium. And this just shows a cross section of it. The heart muscles themselves run in basically kind of these band or spiral shapes. And it does that so we get enough constriction of those areas to push in the right direction to push blood into the next chamber. So the two atria constrict kind of high, which will cause the blood to flow down. The two ventricles kind of spiral from the end up. The only thing I'll talk about is you do have some connective tissue. You don't have to write all of this down, but you have connective tissue to your heart on the outside of your heart, and it kind of helps with not letting your heart overexpand and kind of recoil to your heart. So if you get damage to that connective tissue of the heart, we might get overexpansion of the heart. If we get overexpansion of the heart, we're not going to get the same cardiac output. We're not going to pump the same volume of blood. So it's important that we have that connective tissue that keeps our heart from overexpanding. However, if it gets stiff, we may not get enough expansion to our heart. Cardiac skeleton is basically some of that elastic tissue. Cardiac skeleton, I guess the big thing to know about it is it stabilizes your valves. All right, interatrial septum, what's it do? It's the wall between my two atrium, right? What's my interventricular septum? The wall between my two ventricles, right? All right, our AV, our atrioventricular valves, we had our tricuspid valve and our bicuspid valve, right? Which side of my heart was my tricuspid valve on? Right side. I try it before I buy it, right? The buy it one is also known as the mitral. So if you hear that, we're also talking about the bicuspid semilunars at my pulmonary trunk and also at my aorta. Superior and inferior vena cava are dumping blood back into my right atria. Foramen ovale, what is it? No, not the. Yeah, they're when we're in utero, because we have to go to the lungs to get oxygen when a baby's in utero, right? We're getting oxygen from mom. So there's a little hole that goes between my two atria that just lets blood bypass through from deoxygenated over to oxygenated. Why? Because it's not really deoxygenated here, it's oxygenated. So instead of doing this, it can just go right to there and go out the aorta. We also had a bypass at the pulmonary trunk in the aorta. What was that one called? Yep, you're right. Ligamentum arteriosus. Pectinate muscles. You're on the right track though. Pectinate muscles are just basically when we look in the inside of the chambers of the heart, especially up in the atria, this is where we really name them. You probably saw, it looks like really grooved. You had high points and low points. Those are your pectinate muscles. They're on the inside really of those two areas. We talked about tricuspid. You guys know what the chordae tendineae are in the papillary muscles? What's the function? They prevent backflow, right? Because as the papillary muscles contract, they pull down on the chordae tendineae, which pulls my valves shut. Now blood, as the ventricles contract, blood just doesn't go from the ventricles back up into the atria, because that wouldn't work very well, right? If I did constricted these and blood went down here and then I constricted these and just blood went right back up there, we're not going to get very far, right? So by pulling these valves shut, it allows the only opening to be out the pulmonary trunk and the aorta. So our papillary muscles contract, they pull on the chordae tendineae, snaps my valves shut. So now the blood can't backflow back into my atria from the ventricles. So these guys will contract, pull these, snaps this valve shut. Now the only way blood can go is out the semilunar valves. Oh, and let me show you, this is, oh, it doesn't show it very well on this particular picture, but I will show this part. All these little spongy sort of appearance down in here are called trabeculae. We would see the same kind of thing kind of up in these atrium, and that's what our pectinate is up there. But this doesn't show it. They're barely showing it on the edge right here. And the trabeculae, that's what I was just talking about. It's this sort of texturing on the inside of the ventricles is our trabeculae. We have the moderator band that goes across, stimulates the papillary muscles to contract. It comes from the interventricular septum across the moderator band to the papillary muscles. It shows your chordae tendineae. So this would be my valve. This would be my chordae tendineae. This would be my papillary muscles. And here, this looks very much like what we've seen. Here's a good papillary muscle. Here's our trabeculae. No. Usually they're easier to see. This might be part of it right here. On the sheep heart, it was very, very distinct. And I will pin it on a sheep heart because it's so distinct. The human hearts, for whatever reason, they're kind of hard to see. The conus arteriosus, this is basically, it goes, the bypass point up there. It's at the superior end of my right ventricle. We talked about our pulmonary arteries, pulmonary veins. Everybody good with those? Mitral valve. I'm kind of cruising through these because we've talked about them. Aortic valves. You guys all okay with those? And this shows these guys right here. You can see all our different valves in here. All right, right and left ventricle. I think I mentioned this in lab, but I want to spend a little more time on it. Your right ventricle looks much smaller than your left ventricle, but it actually pumps the same amount of volume of blood. And the reason why is this kind of wraps around the heart like this, where this just takes up this big space. So they really have the capability of holding the same volume. They're just arranged in a way that you don't really see it as much. We don't see as much pressure, obviously, from this side, which is why the muscle wall is so much thinner. Why? We don't need as much muscle, right? Because we're just going right here, right beside the heart. This side needs a ton of muscle, though. Why? Because it's going through the whole entire system. So we don't see the big development of pressure because we don't have to push it very far. And this is what I was talking about. So this would be my left ventricle. When we cut the heart this way, it looks huge, but this holds the same volume of blood. It just kind of circularly wraps around the heart like that. And this shows it from this view. All right. Oops. We talked about regurgitation or backflow. Everybody comfortable with that? Basically, valvular heart disease is basically where our valves aren't working correctly. If our valves aren't snapping shut and working correctly, we can get blood kind of leaking back up. It would be regurgitating back up into here versus going, and probably not all of it, but enough you'd hear it if you were listening to heart sounds. This can come after inflammation of the heart. This can also come from rheumatoid fever, which is really a complication of strep throat. If you get strep throat and it continually gets left untreated, that bacteria can go affect your heart to the point where it damages your valves, and now you have a person with heart disease. That's why it's so important to treat strep. And that's why they'll do like tonsillectomies. I just went through this with my daughter in the fall. She constantly got strep with the COVID lockdowns. Her tonsillectomy got canceled twice. And then in the fall, she got strep. We did 10 days of antibiotics. As soon as she stopped, her strep throat was back. They did 10 days of a different antibiotic. As soon as she stopped, the strep came back. 10 days of a different antibiotic. As soon as she stopped, the strep came back. and they finally put her on a Z-Pack, which finally took care of it, but she was like 45 days on antibiotics before she kicked, so she's now finally got her tonsils out, so. But that's what I was afraid of is, I don't want this. It can also cause blindness. That's why any Little House on the Prairie fans in here? Mary from Little House on the Prairie. So, which it's based on a true story. Do you guys even know what Little House on the Prairie is? You guys are all so young. You're like, what? But it was based on the true stories. And the sister went blind as an adult and, well, as a teenager, I should say, an older teenager. And that's what they said is her blindness was caused from strep throat. What's that? The actual lady, the actress just played her, but yeah, the actual sister went blind, and that's what they say it was from, or strep throat. I did. I didn't say a lot. I didn't talk about blindness or anything, but I was like, we definitely have to go to the doctor and keep after this. So, she's pretty calm though. She didn't get too worked up, but I think I was probably got a little more stressed about it than she did. Okay, I'm gonna stop there. So we will pick up, if you guys remind me, we'll pick up right here. I know I'm cruising through the anatomy really fast. Do you guys feel okay about the anatomy? Okay, that's what my hope was. I will slow way down when we get to the actual physiology and the way the heart pumps, which is what we'll do on Thursday. And we'll spend a little more time on cardiac output and all that good stuff. So, all right, any questions before I turn you guys loose? The auricle is just like the ear flaps. So it's the outer part of the heart that looks like the ears are the auricles, and your atria sit under your auricles. Yes, those are your auricles. Auricle actually means ear. So